Good afternoon, ladies and gentlemen. First, thank you very much for your time this afternoon. I want to thank Open Reality for organising this. My name's Ian Tearle. I'm a Wi-Fi SE for Arista. And today we're here to discuss why all 802.11a XAPs or Wi-Fi 6 APs are not necessarily certifiable. What we find in the industry is that, you know, and this happened in N and this happened in A, we come out with standards before they're ratified and we think we know where they're going and we modify the hardware, we modify the chipset. And interestingly enough, Wi-Fi 6 has not been ratified yet. We don't believe it's going to be ratified till at least November, December of this year. So no one's quite 100% certain that this is the way it's going to be and this will be the way it will work. However, some Wi-Fi manufacturers have been shipping AXAPs for about a year now. And interestingly enough, we need to look at the features that make an AP certifiable and not compatible. And when we say certifiable, we mean when the standard is ratified, we tick all the checkboxes. Compatible means, well, we tick some of the checkboxes, but we may not do A, B, C, or D, but we do X, Y, and Z. So let's have a quick look at this. So I need to move that slide forward, and there we go. So some of the features and benefits of Wi-Fi 6. Wi-Fi 6 is not all about speed. It's not about I can do 6.9 gigabits per second of throughput across the Wi-Fi. It's about improving the efficiencies of Wi-Fi. If we look at AC, if we did a packet capture, what you'd see is you'd see VHT or HT headers. With AC, you actually see HE, high efficiency. So to improve this efficiency, what we're going to start using is we're going to use 8 spatial streams on an access point. Well, actually, you're never going to see 8 spatial stream clients. If you do, they will be absolutely massive. They will be hardwired. There'll be lots of battery, and if you did use it on a battery, you'd probably kill your battery really, really quickly. But interestingly enough, a lot of the features that the 8x8 actually help us to achieve is we can do better transmit beamforming. We use something called CSD, cyclic shift diversity, which allows us as let's say a single stream client, an iPhone 6, for example. What it allows me to do is use a single stream, which will transmit to two of the antennas on an 8x8. And it combines them together, and actually it gives me a little bit more gain. So the access point here is better. But also, and this is in real basic format, it actually allows me to stream the data across both of the antennas, and therefore if I drop a packet, I should be able to recombine the packet, which is going to allow me to reduce retries. It's going to allow me to increase capacity, give me better efficiency, and more importantly, now I can look at larger multi-user MIMO groups, whereas before we were limited between 3 and 4, depending on the AP. We can now look at 8. More users, more capacity. Everyone in the industry is raving about target wait time. I saw an article the other day that said that during the next 5 years, they believe that there will be 15 billion, I'll say that again, billion IoT devices. Well, actually, a lot of those IoT devices are going to have cheap radios in them. They're going to be probably 2.4 gig. They're going to have batteries. So what we want to do is we don't want those devices continuously talking to the Wi-Fi, continuously using our valuable airtime, our resource. We want to be able to target those. So for example, if I buy a Samsung fridge and that Samsung fridge has Wi-Fi, and I go to the fridge and it knows that I take out a packet of sausage rolls, it doesn't have to update my shopping list there and then, but what it can do, if I use target wait time, at the end of the day, the access point will say, what have you got for me? And it will send information back. So we're saving time, we're saving airtime, and we're using the battery and the utilization more effectively. Interestingly enough, there was a study carried out that shows that target wait time will need to fully utilize the multi-user capabilities provided by AX, you know, the uplink downlink OFDMA and the uplink downlink of multi-user MIMO. Now, You need to bear this in mind if you're going to do if you're going to do IoT, or you have any plans for IoT for the future, that you need to support uplink and downlink of OFDMA and multi-user MIMO to get the best features out of target wait time. That's interestingly enough. If we start looking at the uplink downlink scheduling, we need to look at trigger frames, etc. We have to put more performance, more efficiency into this. BSS colouring, or BSS colouring helps fix one of the major problems that we have within Wi-Fi for co-channel interference, because if I have two APs on the same channel talking at the same time, that creates co-channel interference. So we'll go into that a little bit more. That's going to help us again. 1024 QAM, better data rates, fantastic. I can talk quicker. Long guard intervals. Well, actually, this is interesting because currently we have a 200 or 400 nanosecond short guard, long guard interval. And what we need to do is we need to improve that long guard interval for primarily outdoor environments. For example, if I'm in an outdoor environment with shopping centers or lakes, whatever, I get a lot of reflection. I get refraction. I can send one packet, and then I send two packets. However, packet one may have taken a different path from the other packet, and it would arrive at the AP or at the client at before the original packet was sent. It's what we call inter-symbol interference. So by having a longer guard interval, we can reduce that. We're going to improve the resiliency of the Wi-Fi. Longer IFDM symbols, again, at the edge of the cell, we're improving client connectivity. We're improving the client speed to Wi-Fi connection. Because as we all know, the further we move away from a Wi-Fi access point, the slower the data rates. The slower the data rates means I have more effect on my Wi-Fi network. Preamble puncture is something that is not necessarily you need to do it. It is part of the standard. It's an optional capability. It has to be supported by both the client and the access point. But basically what that allows us to do is, if we're looking at using 80 megahertz or 160 megahertz wide channels, and yes, I know a lot of you are sitting there now quietly laughing and smiling away going, you'd never do that in an enterprise environment. That's a really bad idea. Maybe so with a preamble puncture. What we can do is, instead of us using the primary channel, we use the secondary channel on that 80 megahertz wide channel or the 860 megahertz wide channel, and therefore we can actually use some of that channel width. Now, as I said, it's optional. It's part of the standard, but I want to be able to use that because it allows me to use more efficiently the spectrum, the airtime utilization, the air that we have around us. We have only a limited amount of time. And when we start looking at the what we call multi-user ready to send, what we do is we send the capability to reserve the medium and the nav timers, but we send that in OFDM only, because we need to make sure that all the legacy devices on the network understand what that packet means. It means I'm reserving S time slot, because now what I want to do is I want to do a downlink OFDM exchange. I need to synchronize these devices together, but the legacy devices can't transmit. It also allows me to synchronize the uplink for CTS responses. So the AP uses it as a trigger frame to allocate the subcarrier. That allows us to use the air more effectively. Okay. Now, bear in mind, a trigger frame has to be supported again by both the client and the end user device. I'm going backwards with my buttons here. My apologies. Also, guys, there's a chat box in the screen. If you do have questions, we'll take the questions at the end. Just feel free to fill in those questions, and I can have a look at those at the end. QAM. It's a modulation type. The modulation type allows us in turn for the data to be communicated through the air. The more complex the modulation, the more the data rate. Now, if we look at 256 QAM, we had to be within 10 to 15 feet of an access point, and the air had to be really, really clean. You know, very little co-channel interference, a really good signal and noise ratio. So in theory, if I'm going to use 1024 modulation, I need to be a lot closer to the access point. Well, maybe not. So what we've done is we've got 8 bits per symbol on 256, 10 bits per symbol on 1024. We've got a 25% data rate increase. More data equals more capacity. Now, bear in mind that when we use a 1024, we're going to use something called OFDMA. OFDMA Uplink and Downlink requires us to use something called resource units, and I'll explain about resource units shortly. But resource units should, and I state this should, allow us to increase our signal to noise ratio and therefore improve what the client actually hears, because we're increasing that signal to noise ratio. Okay, smaller channel widths. I said earlier, it's not about speeds and feeds and stuff like this. If we look down here in the corner, you know, this is a single spatial stream device. This is your iPhone, let's say. An iPhone with a single spatial stream using an MCS index of 11, the short guard interval of 800 nanoseconds might get 1.2 gig. Okay, that's great. Well, the chances of us ever using 160 megahertz wide channels are very slim, unless we use the optional puncture preamble, and then we need to be in a quiet RF environment, again with 80 megahertz. So let's be realistic about this. Let's move this down to a 40 megahertz channel, and let's use 286. Well, actually, what that does is, if I'm now with OFDMA, what I'm doing is I'm actually I can get 9 clients onto a single channel. Well, in theory, I could get I think it's about 2.5 gig of throughput across the air from multiple channels. Interestingly enough, I've got a 50% radio header over there. So really, probably talking about 1.2 gig. So that's great. And of course, that will increase as we increase our number of users. Now, bear in mind that most of the devices and most of the packets that we see across the network are anywhere between 256K and 512K. And yes, this is primarily for voice as well. So why do we need this? It's important that we be able to use efficiently the airtime. These modulations allow us to back off, listen to noise, give us better data rates, because this, you know, if I'm hearing a lot of noise with 256 cram, I can back this off down to a 64 cram and still get 172 meg. That's a great data rate. I think I covered off earlier there about the guard intervals. We see here our guard interval has gone from 800 to 600 nanoseconds. Now, let me explain how OFDMA Uplink and Downlink works. This is probably the most important high efficiency standard that we have in there. This is going to help us change the way we work from a Wi-Fi perspective. We were talking about multi-user MIMO. Multi-user MIMO has been around since 802.11ac or Wi-Fi 5. Interestingly enough, well, it didn't really work. If we look at any of the iPhone devices, none of the iPhone devices supported multi-user MIMO. We had a problem with grouping those devices together. Those devices had to be 15 to 20 feet together. So what actually happened is this. I have a device. That device wants to transmit data. Email, I'm downloading a movie, whatever. I'm going to take up the whole 20 megahertz wide channel to transmit my 512K. I take the whole channel. That's an inefficient use of the airtime. So the way that OFDMA now works, and if anyone's of interest, is orthogonal frequency division and multiple access. Okay. The way this works is we're actually changing this. So instead of having one wide load, I can break the 20 megahertz wide channel down into what we call resource units. In this model, we had 64 subcarriers. In this model, we actually have 256 subcarriers that allows us to break down the channel into 9 resource units of 26. Well, actually, what I can do then is if the client decides that he wants to reserve a time slots, and these guys here want to transmit a video, these guys are going to get more time slots. They're going to get more larger resource units. So they might get 52 resource units, whereas this guy here who's just sending an email might only get 26 resource units. So OFDMA allows us to take the 20 megahertz wide channel and break that channel down into smaller chunks, and therefore we can get more vehicles on the road, we can get more transport, we can get more people communicating. The importance of this now is that Wi-Fi is becoming more and more prevalent across the world. You know, you go anywhere, there is Wi-Fi. You go to a hotel, you go to a conference, you go to a school, you go to a university, you go to a conference room, and if you have one guy wishing to take up that whole channel because he's downloading a movie, that's an inefficient use and resource allocation of resource. However, if I can break the channel down into a smaller resource units, now I'm using the channels more effectively. But that doesn't actually help me when I only have X amount of channels that I can use. For example, within the 2.4 gig standard, we only have 4 channels we can use in the UK. And yes, I know that's a contentious point, but actually we could use 159 and 13. Would you use 159 and 13 in a busy city where most of the channels are on 16 and 11? Of course you wouldn't. But if you were building a hospital in Truro and it's in quite a clean RF environment, why not consider using channels 159 and 13? So if we look at this, if I'm on channel 36 currently and the 5 gig frequency, I can hear all of these other people around me talking. The way to look at this is dinner tables. I'm having a dinner table conversation here with my colleagues. I can hear all of these guys talking. They're all on the same language as me, channel 36, but they're talking loud enough that I have to wait until this guy here has finished transmitting before I can actually reserve the air, get on the air and transmit my data. So in theory, this could be my office, this could be my office, this could be my office, but this could be McDonald's next door, because it's an unlicensed frequency. Anyone can use the channels. Of course, we have the laws to abide by that says I'm waiting, now it's my turn to transmit. Well, actually, one of the things that we're going to do with BSS colouring is this. Well, if we combine this together with OFDMA, now what I can do is I can take my 2.4 gig channels and I times that by 63, because actually I've got 63 colours, and it's not a colour, it's 0 to 62, that I'm allowed to use as a number. So channel 1 will have number 1, channel 1 on, so number 36 here might have 1, 36 here 2, 36 here 3, 36 here 4. So now, if I hear any one of these tables talking and it doesn't have 36/1 enabled on it, I know it's not my dinner table. I can carry on having my conversation. This means now what I'm doing is I'm reducing co-channel interference. Co-channel interference is a major issue with us if we build our Wi-Fi networks wrong and we have too many APs on the same channel. Well, actually, this is helping us reduce this. So now, in theory, if I take my 24 5 gig channels and I times them by 63, I have 1,512 colors of separation that I can use. In theory, that should allow me to have 1,512 different channels and different colors and different conversations. Now can we see where this is going? This is giving me a lot of density, a lot of capacity, and a lot of efficiency. There's a little problem with this though. And this little problem is we don't have many of these Wi-Fi 6 clients yet. So we still have to wait around and we still have to use the legacy Wi-Fi 5, the Wi-Fi 4s. Some cases we're still seeing Wi-Fi 1, B clients, BG clients on the network. But Samsung have released the S10 and that's a great little device. You can see here that this is a PCI card for a fixed Wi-Fi machine. And this is an AX200 card. These are all supported. I can go out and buy one of these cards right now and I can put it into my laptop. But will it support all of the aforementioned features that I discussed? Maybe, maybe not. We're hoping that Apple, when they release their iPhone 11, that may have an AX chipset and may support all of the latest features. You know, Apple usually release around about September time, so we'll see what happens. Now, so if we look at some of the other platforms that are out there. Now, bear in mind, I represent Arista. We're not all the same. We're all different manufacturers. There are some manufacturers that have bought APs out to market that follow the what we call the certifiable, and there are some that are brought out the comparable. But what we want to look at is what isn't supported on an AP. If you actually look at the data sheets, you know, we've based this documentation and this information on the vendor's data sheet. This is not us guessing. We know that some of them don't support BSS colouring. We know some of them don't support the uplink or downlink of OFDMA or multi-user MIMO. They might actually support downlink, but not uplink. This is a major efficiency. This is a major stumbling block that stops me from having the most efficient Wi-Fi network I can build. So when we drill down into this a little bit further, what we want to do is we want to see an access point that gives me everything. Excuse me, guys, my apologies. Interestingly enough, you'll notice that our access point isn't shipping yet. Our access point isn't shipping because of this specific chip that we waited for. This specific chip is a Hawkeye version 2 chipset. A lot of manufacturers have used Hawkeye version 1 or 1.1 or 1.2, which in some cases does not have multi-user MIMO, doesn't have the capability to do OFDMA. It's a hardware limitation of the chipset that is stopping them from being certifiable. If we look all the way down through our APs, we can see here we've got an 8x8 and the 5 gig 2.4 here. We have a third radio that we use for spectrum analysis. We have BLE, we have all the standard stuff. We have the capabilities. Well, and remember this, you can buy AX access points right now and you can plug them into your AF switches or your AT switches, but you will lose some of the capability. And that's all manufacturers. That's not just us, that's every manufacturer. So, what we want to consider is when I am looking to buy Wi-Fi 6 access points for my network, I need to make sure that certain things, I need to make sure that the chipset that is within my access point supports all of the features. I need it to support OFDMA. I need it to give me the capability to split the channels down into smaller resource units and get more users on the air and get them off the air faster. I need to make sure that if I am actually buying an access point that is to go into the enterprise environment, a hospital, a college, a large school, that my radio and my AP radio is built for enterprise. If you look at these radios, and this information again is on the data sheets, these are residential radios. These are designed for small home office environments. Would you want to put one of these into your corporate environment, into your enterprise environment, or your university environment? You have to start looking at these now, because now that makes it uncertifiable. Uplink OFDMA. We're looking at any form of high density. The number of devices, as I said, is going through the roof. Target wait time is going to support this. If I don't have uplink multi-user MIMO, I'm not going to see all of the features of target wait time. Again, look at your chipset. If you look at them, the BCM, these are the Broadcom chipsets, not expected to support uplink multi-user MIMO, and it cannot support an 8x8. My question would be, why would I put this into the middle of my network if it didn't support all the latest features? So I'm going to actually look at the questions board now, because I did promise that we're going to try and make this quick and easy for people. Does anybody have any questions?
Hi, Ian, it's Sam here. When's the C250 going to be available?
C250 is shipping in August, September.
Okay, so imminently then.
Yeah, imminently, yeah. So we've got it, it's all ready, it's all standards based. We believe that there might be a slight change on something called Agile DFS, but that again, because we have the hardware, we have the memory, we have the processing capability, it's just going to be a software change. So we do have a quick poll here, and I'm going to just launch this quickly if people can quickly ask this. Does anyone, can I just ask you quickly, just to quickly consider whether you bought AX, whether you're considering buying AX, Wi-Fi 6, sorry, I'm old school. Wi-Fi is something that Wi-Fi 6 is something that is massively required in the marketplace. Wi-Fi has been a big challenge over the years for Wi-Fi engineers like myself, because we do bang our heads against the wall a lot of the time because too many access points can be put up in the air, too much airtime. I just want to know where we're looking at. And actually, it's looking quite interesting that 50% are considering the Wi-Fi 6 now. Some people have already purchased Wi-Fi 6, which is great. It would be interesting to know how you're finding it because of the client issue. We don't have a lot of clients. We believe that to see the improvements of Wi-Fi 6, you've got to have at least 30% of your clients on the network using Wi-Fi 6. So, guys, is there anything else that I can answer, or are we done for the day?
We do have some other questions, Ian.
Yeah, please go ahead.
Actually, there more comments really. Mark's saying thanks for a really useful webinar. A couple of other people saying that they don't have Wi-Fi 6 clients yet, but they're planning to refresh, I guess, the network next year.
Yep.
And again, somebody else saying not considering it until there's a better client population. So obviously, a few people holding off yet, but obviously this webinar will put them in a good stead when they do come to select an access point.
Okay, guys. First, thank you for the comments. Hope it's been of use to you. Again, thank you to Open Reality for hosting this for us. Hopefully, we'll do some more lunch and learns. I know that time is precious in our industry. I've given you back 3 minutes of your day. Thank you very much, guys. Have a good day. And I sign off now.
Thanks very much, Ian. Thank you, everyone.
Cheers. Bye-bye.
Bye-bye.